Hi everyone, I'm Professor Burgasser, and in this video we're going to be looking at the forces that come about when you have an object interacting with a fluid. And these forces are viscosity, buoyancy, and pressure. And as we'll see, these forces are very common in the world around us because we are standing in a fluid as we speak, in the air. But of course, as we interact with other fluids like water, we also see those forces acting on objects that are either submersed or floating on the top of these fluid bodies. Now, viscosity is our first force, and that is a dissipative force just like friction, and it acts to slow down an object as it moves through a fluid. The way it really works is that as an object moves through a fluid, it has to sort of push that fluid around it in order to make for space going forward. And that act of pushing or moving the fluid around causes a lot of dissipation. You're exerting a force on the fluid to move it around, which means that there's a force acting back on the object to then slow it down. So this interaction between an object and the fluid ends up reducing the speed of an object because the viscosity acts in the opposite direction of the motion. So we can draw that on our diagram here. If we have an object moving forward with some velocity, the viscous force, the drag force, is acting in the opposite direction, and in that sense it acts exactly like friction. However, unlike friction, viscosity actually depends on the velocity or the speed of the object through the fluid. And so we actually have two quantitative forms for this force, one at which at low speed the viscosity or drag force is proportional to the speed of the object through the fluid. And so we write this as minus b, which is a constant, times the speed, and then times the direction, all right, that v hat is signifying the direction of the motion. And of course it's minus v hat, so it's in the opposite direction. So if velocity is moving in one direction, the viscosity force is actually pointing in the opposite direction to slow it down. At sufficiently high speeds, we actually get a much steeper dependence of the viscous force on velocity. It depends on velocity squared, and we have a slightly different force constant in front. But in the end, that constant is based on the properties of fluid, the shape of the object as it moves through the fluid, and those two terms are compacted into this one constant that describes how things move through fluids. Now, because this viscous force or drag force increases as you get to higher velocities, for an object that's falling through the air or falling through the water in any kind of fluid, you have a possibility for having a terminal velocity, a velocity beyond which the object can no longer go any faster because it is actually being dragged by this drag force. And so in the case of, for example, parachuters jumping out of a plane, they have a force of weight acting on them, the interaction between the earth and their bodies through their masses. And if they're falling downwards, they're going to have a viscous force, a drag force, that's pointing in the opposite direction. At some point, they're going to reach a velocity in which that drag force is exactly equal to the weight. And at that point, the forces are equal and opposite, and so they cancel, and you end up with a fixed velocity, a terminal velocity, that depends on the weight and these constants that describe how an object moves through a fluid. Now, notice that the terminal velocity depends on the weight of the object or the mass of the object. And this is exactly why Aristotle, when he did his experiments looking at how things fall through water as a fluid, he found that heavier objects move faster as they fall down. That's because the experiment was dominated by this viscous term, this terminal velocity. But in fact, that's an interaction between the fluid and the object. It doesn't have to do with how the Earth actually pulls down objects through gravity. Now, nature actually takes advantage of this faster fall through heavy objects, or actually slower fall for lighter objects. Very small animals such as spiders and ants have extremely small terminal velocities because those drag forces or viscous forces are extremely high and actually turn out to be much greater than the weight if you move at high enough speed. So spiders, for example, can float through the air, and they're literally falling, but they're falling at such a low speed that they can essentially glide because of this viscous force. Whereas bigger animals like ourselves, or even heavy, dense rocks like meteorites, will have extremely high terminal velocities, and these will literally be terminal velocities because we cannot survive an impact at 50 meters per second, which is something like 110 miles an hour. And then there are animals that are sort of in between. Mice and cat, there's lots of speculation or sort of anecdotal stories about cats falling from large distances and surviving. they are right at sort of the cusp where perhaps the terminal velocities are so small, particularly if they spread their arms out and they increase their drag coefficient, then they can actually reduce their terminal velocity to the point where they could survive an impact. Right? But very small animals, like insects, particularly take advantage of this so they can just glide through the air. And there's really nothing you can do to the ant in terms of dropping it that will actually kill it because its terminal velocity is so small. Now another force that happens with the interaction with objects and fluids is the buoyancy force. And this is the force that emerges when you place an object in a fluid and that fluid is displaced by the presence of that object. So it's very similar to viscous force, but this can happen in a static sense where you actually displaced or lifted a fluid up because you've placed a heavier object inside that fluid. It takes work or takes force to push that fluid up, and because the object is applying a force to push the fluid up, the fluid is also applying a force to counteract that motion, and that will actually point in the opposite direction of surface gravity. Now we see this buoyancy force most commonly when we have a closed container like a bathtub. And in fact, it was really first explored by Archimedes when he was trying to measure the density or the mass of a crown, which turned out to be not made out of gold. He was able to figure this out based on this buoyancy force. And he did it by looking at the displaced fluid. And it turns out that the force is exactly equal to the displaced weight of the fluid, all right? Mass of that displaced fluid times g. So if an object is floating on top of a surface, there's going to be a little bit of displaced fluid, and that little bit is the buoyancy force that counteracts the mass of the object and keeps it suspended on the surface. If an object is completely submersed, then that displaced weight of fluid is just the density of fluid times the volume of the object. Now, buoyancy and weight, as I mentioned, can counteract each other, and this is particularly important when we're immersed in fluids. Any object that's immersed in a fluid is going to have both a weight and a buoyancy term, and buoyancy always acts in the opposite direction of surface gravity. So these terms are always acting in opposite directions. So if we look at this scuba diver, the scuba diver has a weight of mg and has a buoyancy force that's equal to the displaced fluid, the density of fluid, times that person's volume, times the surface gravity of the Earth. Now, we can rewrite our mass times g to be equal to the density of the scuba diver, the average density scuba diver, times his volume, times surface gravity. And when we add these forces together vectorially, we see that the net force acting on the scuba diver is really just the difference in the densities of the fluid and the scuba diver times the volume of the scuba diver times surface gravity. So whether we float or sink in a fluid really depends on the differences in the densities. And of course, since our bodies are made mostly of water, it turns out that we are very close to float in water. So it kind of depends on our individual bone densities and mass indexes. But on average, humans are slightly more dense than seawater, and which means that we very, very slowly sink if we sit in water. Of course, if we breathe in air, we're lowering our density, and that will cause us to float up. So we and many other animals, including sea animals, have densities that are very close to water, which causes them to become essentially weightless as they're passing through the water. Now, of course, right now, standing in the air, I am immersed in a fluid, which is the air, and I don't feel as strong of a buoyancy force, mostly because the density of air is so low. It's about 1,000 times lower than that of water. And so the buoyancy force of air on me is not that great. But of course, if we're looking at a very low density object, like a bubble, for example, or a balloon of helium, then in that case, the buoyancy force is enough to force that object to go upwards as opposed to downwards. Now, our third fluid force is the pressure force, and this is a compressive force that acts perpendicular to surfaces of objects. And that compressive force is really coming from the random interactions or random motions of the atoms or molecules that make up that fluid as they bounce off the surface of our object. And this is something that depends on the various factors of the gas or fluid we're talking about. It can depend on the temperature, the density, or the composition. But in all cases, this is something that's acting perpendicular to the surface, whatever surface is exposed to a fluid. Now, pressure is really a force divided by area. So if you want to calculate the force, you have to multiply the pressure, which is a scalar term, times the area of the surface that you're looking at. And then keeping in mind that that pressure is going to act to compress or push against that surface. It actually acts in the opposite direction of our normal force, for example. Now, if we look at the action-reaction pairs, if I have a gas, in this case, if I have a gas that's acting on the outside of our box, the pressure force is pushing in the box. The equal and opposite reaction force is actually in the box pushing back against the gas. And that's what prevents the gas from getting into the box. If there was no force there, the gas would just go right through. Similarly, the gas that's in the box, maybe it's at a higher pressure, is pushing the walls of the container outward, and the action-reaction force is the walls of the container pushing back. And this is exactly the case when we have a balloon such as this. So the pressure I put into the balloon is pushing the balloon walls away, but the elastic force of the balloon is actually counteracting that pressure. So even though I have a higher pressure inside this balloon, which means I have a higher force per area, the difference between the outer air and the inner air is counteracted by the elastic force of the balloon. Now, pressure is an extremely important fluid force for the body. One of the most important cases is the blood pressure that's present in our body. That blood pressure is generated by the pumping and valve actions of our heart, and it allows blood to flow around our body and, of course, deposit nutrients and collect waste as it moves. Now, just like the balloon I just did, our blood vessels are extremely elastic. It's a fairly complicated layering system, particularly our arteries and veins, our major arteries and veins. And that elasticity is important for keeping the blood pressure regulated inside our body. Now, we have several diseases in which blood pressure can be affected, particularly when the elasticity of these arteries and veins is affected. Arteriosclerosis is a good example. The sort of plaques and calcifies that are built up into our veins and arteries can cause that elasticity to go away. And without an elastic frame, a wall, to keep the blood pressure contained, you can get all sorts of dangerous effects, including heart attacks, when those blood vessels rupture. Now, we also have to consider from a body perspective that we have pressures internal to our body and external to our body. Right now, we are in a pressure from the atmosphere. A lot of that has to do with the weight of the atmosphere above us pushing down, but the pressure of that air pushing down on our bodies has to be counteracted by pressure, positive pressure, from our bodies pushing outwards. And a lot of that pressure again comes from the contained of the elasticity of the cell walls in our cells themselves. Our cells have their own internal pressure called turgid pressure. And in the case where we go into a low pressure environment, that can be very dangerous and cause rupture of cell walls and of course arteries and veins as well. On the other extreme, those of you who have ever done scuba diving know that the pressure underwater gets higher much faster than it is in the air. And there are limits to how deep humans can dive because of the extreme pressures that occur at very, very low depths in the ocean. And so the pressures of the external and internal environments are things that we always have to take in consideration when we're looking at the health of the human body. Now, it turns out pressure is also important for rocket motion. One way of imagining a rocket, for example, an air rocket or a water rocket or even a real rocket, is that you have a container of very high pressure gas, and that container is initially sealed. In which case the gas, because it's high pressure, is pushing outwards, pushing against the surface of the container, so those pressures are pushing the container outward, whereas the container's action-reaction pair is to push that gas inward, to keep it contained. Now, if all of these four walls are secure, that means that all of these forces are in balance, and so you would just keep this gas contained within the container. But as soon as we open one of the sides of the box, you can see that we have an unbalanced force. We've got an extra force of the container pushing the gas downwards, which is going to force the gas out. But on the other side, we have the unbalanced force of the gas pushing the container upwards, which forces the whole container upward as well. And this is the basic principle for rocket motion, such as large rockets, such as the SpaceX rocket.
3, 2, 1. Ignition sequence start and liftoff of the SpaceX Falcon 9 rocket.
So to summarize, when objects are in fluids, they experience three different forces acting on them: viscosity, buoyancy, and pressure force. the viscous or drag force always acts in the opposite of the velocity of the object through the medium. So it very much acts like a friction or a dissipative force. But in this case, viscosity or drag force actually depends in magnitude on the speed or velocity itself. And it depends whether it's speed or speed squared is based on how fast that speed is, whether it's low speed or high speed relative to the fluid. And because of this speed-dependent term, it's possible to have a terminal velocity for an object that's falling in a fluid, falling with respect to a gravitational vector. And so that terminal velocity, that terminal speed, is dependent on the weight of the object. And this is exactly why Aristotle got the falling objects of different weights wrong. He was actually measuring viscosity and not gravitational acceleration. The buoyancy force also counteracts gravity, but it counteracts gravity in all cases because it happens when you displace a fluid, when an object displaces a fluid. And the buoyancy force magnitude is simply equal to the weight of the fluid that is displaced. So if an object is floating, it's part of the volume of the object times the fluid density. If it's fully submerged, then it's the total volume of an object times the fluid density times surface gravity. That's the weight of the fluid that's displaced. And you can have the case where you have the density of an object and density of fluid being very close to each other. In that case, you have what's almost similar to weightlessness, and this is what we experience when we swim underwater. Our third force is pressure force, and that is a force that compresses on surface of the object. It acts normal to the surface and presses it in. And this is a fundamental force in how our bodies maintain homeostasis, but it's also something that we see in rocket motion. How we push gases out at high pressure also has a counteracting force of pushing the rocket upwards.